Okay, in this lecture, we are going to be looking at the last hypothesis test for the project. So this particular hypothesis test is the chi-squared test for independence. In this particular situation, we are looking at we're looking at different industries and the job openings in different industries in a particular city compared to the national average. And the question is are the job openings that are in this particular city in these industries reflective of the proportion of job openings for the national average? So you can notice in this yellow box right here, this data allows you to compare the proportionate frequencies of job openings in the independent categories of industries in Houston compared to the proportionate frequencies of job openings in the independent categories of industries in the nation. So right away, we've got the number of job openings, we've got the relative frequency of job openings, and we're going to come over here and determine what it is that we're doing. So we've got what is the test statistic that we're running? We're running chi-squared. What is the alpha? Once again, I like to run a 0.01 alpha, especially when we're dealing with numbers this large, the number of observations, because if you have this many observations, you might as well run a large alpha, or rather a small alpha. The number of categories, coming right over here, we've got 8 categories, which means that we have 7 degrees of freedom. And then the next question is are there equal or unequal proportions? In other words, do we expect do we expect them all to be the same, or do we expect them to be different? And because we're comparing them to the national average, we're expecting them to be different. And then lastly, what's the total number of observations? And that's the total number of observations in this sample. And so that is 11,403. So now what we're going to do is we are going to copy this information. So I'm going to copy this first and press Control C or Command C if you're on a Mac, and come all the way over here, and I am going to press Control V. So and then I'm going to paste just the values, as I only want the values. And I have, what am I going to put right here? Occupation categories. And so we have the observed frequency for all of those. Now, there's 2 ways to determine what it is that we're going to do to say, hey, this is what we expect it to be. I'm going to show you the first way, which is you can come right over here, and we're going to press Control V right here. And I already determined the relative frequency. So these are all the relative frequencies of these individual observations. So you have national observations, and then you have relative frequency. And in order to find the expected frequency for all of these, what we're going to need to do is basically put the relative frequency proportionate to this total right here. So for instance, I'm going to do equals this relative frequency multiplied by the total number that is in the observed frequency column. Same thing right here for the architectural, equals relative frequency multiplied by the total frequency, equals relative frequency multiplied by the total frequency, and one more time, equals relative frequency multiplied by the total frequency, which we can do this all day, or we can go like this and say, okay, I want, let's see, total frequency. We're going to just do there we go, and just drag it down. And so if you notice that this is 11,403, this is also 11,403. And so that is how you calculate the expected frequencies. And so then you can put the original values right here. Control C. And then you can also see it actually calculates all the relative frequencies for you when you put the original values right there. So that is how you calculate for the expected frequencies. I'll make sure that the two of these add up together, and then you'll be good to go. Next, so we've got the chi-squared now because it did all the rest of the calculations for you. So we've got the chi-squared, so I'm going to copy this. And I'm going to bring it right here, and I'm going to paste it. Paste just the values. And what is the probability of this occurring? Once again, we can do equals chi-squared inverse right tail, and put the or better yet, sorry, chi-squared distribution right tail, and then we're going to put right there, and then the degrees of freedom. So we put the chi-squared in first, and now our degrees of freedom is going to be 7. So we've got 7 degrees of freedom. And so it's 0, which I actually already have it calculated for you right down here. But I also want you to know, hey, you can do that fun little formula, equals chi-squared distribution right tail, and then putting in 15,000, and then the degrees of freedom of 7. And so you can do that, and it'll give you the same answer. So it's not too bad. And I'm going to make that in white just so that you guys can see that. Next is the, so we got the degrees of freedom of 7. And then the research question. Once again, I just come down here, goodness of fit, unequal proportions, otherwise known as test for independence. What is it that you want it to do? Compare observed frequencies and categories to those frequencies that would be expected in a sample, followed by a known or hypothesized distribution. That's what we're doing. Okay, we have a known national distribution. So this is the known national distribution right here, and we are comparing the sample to the known national. And when we compare the two, we want to know, are the proportions the same? Okay, so is the proportion of job openings in the Houston area reflective of the proportion of job openings nationally by job type? Okay. And then the purpose of running the test to determine if the observed proportions of job openings in Houston differs from a known proportion of distribution in the United States by job type. And once again, I got that from right here. The purpose is, I just copied and pasted it, and then I modified it for this. Then what's the anticipated outcome? It's anticipated that the Houston job openings will be different. Okay, so now we're going to go into assumption 1. Assumption 1, what is the one categorical variable and what are the categories? So the one categorical variable is types of jobs or industries. Okay, so we've got industries. And the categories inside of industries are accounting, legal, I literally just copied and pasted all of these. I went Control-C, and I pasted them into there, except you can't do it quite like that. You've got to copy each individual set of text and put it in there. Next, assumption 2, describe how you know that each observation is independent of each other. Basically, a job falls into one of those categories. It cannot be in more than one category, therefore they are independent of each other. And then assumption 3, ensure that the expected frequency is at least 5 for each group. And when we look over here, we're coming to the expected frequency categories, and you'll notice which one is the smallest one. The smallest one right here, that is expected to be 609.75. So therefore, the minimum expected is 607.725 or 73, which is above the minimum of 5. Another thing that I want you to do right now is we already have a relative frequency distribution, so you don't have to make the relative frequency distribution, but I want you to come right here and say, okay, insert bar chart. And we're going to have a bar chart right here. And so we've got Houston job openings compared to national proportions by industry. And so we've got this wonderful chart, and that's all that you've got to do without, but bring it down here, which I already had it down here, but I'm going to delete, press Control V, and you've got to know how to interpret that as well, right? So you've got the orange, which is, that's what's expected by the national, and then you've got the blue, which that is what's actually occurring in Houston. So observed frequencies, you could even adjust this and say observed frequencies in Houston, expected frequencies from national proportions. And then right down here are the frequencies between each group expected to be equal or proportionate to something else. If so, explain. So like we said earlier, we are expecting it to be reflective of the national proportions, so just put in there what you're comparing it to, what distribution you're comparing it to. For the null hypothesis and for the alternative hypothesis, you can literally go to the goodness of fit for unequal proportions, and there's an example of the null and the alternative hypothesis right here, and you can copy these and go back to yours for the null and alternative hypothesis, and you can just let's put it right here so you can see it. There is no difference between the observed values and the expected values, and right here it says there is no difference in the proportion of Houston job openings and job openings nationally, and then down here there is a difference between the observed and expected. Then right here the proportion, you can write it, there is a difference in the proportion of job openings in Houston compared to the proportion of job openings nationally. And so it's pretty much the exact same thing as what that is. You just put in your dependent and independent variables and you're good to go. So for the test critical value, in order to determine the test critical value, remember the critical value is when you hit that value, anything beyond that value means that there is a difference between the observed and the expected. Anything before that value means that there's not a difference, or anything beyond that value, you reject the null hypothesis. Anything less than that value, you fail to reject the null hypothesis. So one thing that you can do here is use the chi-squared table. And for the chi-squared table, you use the alpha level, which this is the alpha level right up here, and then you've got the degrees of freedom. So the degrees of freedom is right here. So 7 degrees of freedom is what we have, and then the alpha level is 1. So now we've got, or 0.01. So now we have the intersection of the two is going to be 18.48. So let's put 18.48 here. Or you can use this fun little chi-squared inverse right tail formula, and we can do equals chi-squared inverse right tail, and put the alpha level, and then put the degrees of freedom, which is 7, and it'll give you the exact same thing, just even more accurate. And then I'm going to copy and paste just the values. So you notice how the it's not 18.48, it's 18.4753061, which is even more accurate. Which brings us to our decision rule, where we reject and are failed to reject. Remember, I said with this reject and failed to reject decision rule, we are going to reject the null hypothesis if the chi-squared calculated is anywhere from the critical value to the right. We are going to fail to reject the null hypothesis if the calculated value is anywhere to the left of the chi-squared crit. Okay, and so that's what we're writing right here. If chi-squared calc is greater than chi-squared crit of 18.475, then we're going to reject the null hypothesis. If chi-squared calc is less than or equal to 18.475, we're going to fail to reject the null hypothesis. And really all that you have to do for yours, just copy and paste this and just put the the critical value in right there, and it's going to be correct. Okay, it's just that delineating point that allows you to make a decision. Also, so what's the Testcalc value? In order to determine the Testcalc value, all that you got to do is come over to this fun little chart that we already made, this contingency table with the additional calculations. And if you go down to the bottom, it should have already calculated the chi-squared calculated value for you. It looks at the difference between the observed and expected, you square it, and then you divide it by the expected scores, and then you add all those together to give you the chi-squared calculated value. So our chi-squared calculated value is 1526.0178, so I put that right there. And what's the probability of that? Well, I would write it as p is less than 0.00001. The other way that you can do this is equals chi-squared distribution dot right tail, and then we're going to put the chi-squared calculated value right there, and then we're going to put the degrees of freedom right there, and that gives us 0. Okay, but once again, I don't like putting 0 because obviously anything's possible. I like putting something to the effect of p is, the probability of this occurring is less than 0.00001. Okay. And so next, is this statistically significant? In other words, is p more extreme than the alpha? That's what we want to know. When you see the term statistically significant, what we're doing is we're comparing p to alpha. When you're saying make a hypothesis decision, you're comparing the values, the test values. So right here for the statistical significance, that's talking about the p-value. As the p-value of less than 0.00001 is less than the alpha value, the results are statistically significant. That's all that we're looking at. You're comparing p to alpha, and if p is more extreme than alpha, then it is statistically significant. If p is greater than alpha, then it's not statistically significant. It's as easy as that. Next, making a hypothesis decision. Like I said, compare the test calc to test crit value. Let's do this. So when you have the test calc of 1526.078 is greater than 14.067, the decision is to reject the null hypothesis. Okay, so just put your numbers in here and then say if chi-squared calc is less than or less extreme than chi-squared crit, here, then Control C, chi-squared crit of 14.067, the decision is to reject the null hypothesis. Chi-squared calc of 1526.078 indicates that there is a difference between the proportion of job openings in Houston and the national proportion. That's all that it does. Chi-squared calc, the only thing that it does is tell you there is a difference somewhere. It doesn't tell you where the difference is, it just tells you that there is a difference, which once again is a reason why chi-squared in and of itself, when running it like this, is kind of useless, because it's just like, there is a difference. Great, I'm so glad that you told me that there's a difference. Can you tell me more about that difference though? And that's where chi-squared, the percent, interpret the percent of chi-squared for each individual category. And so we're going to look at the individual categories. And so we only care about the categories that are above 10%. I really don't even care about the one that's 10%, but if you want, I'll highlight that one too. Some people I guess would. But you've got, I didn't want green, I want yellow. You've got 54% of the difference of the chi-squared calc comes from architecture and civil engineering, 10% comes from computer software and hardware, and 29% comes from internet and tech. So you look at these and you're like, is it above 10%? If it's above 10%, then you need to look at the difference scores. So you got the difference scores and you say, okay, I've got this difference score of 708, which means that it is more than what was expected. In other words, the observed scores in Houston are more than what's expected based on the national proportion. Then coming right here, computer software and hardware, this is less because it's negative. less than what was expected. And then next, internet and tech, once again, in Houston, the number of job openings in tech is less than what's expected. And so coming back over here, interpret the percent of chi-squared. Okay, by interpreting the percent of chi-squared, 54% of the contribution is attributed to the difference between Houston and the national and the nation in architecture and civil engineering. Okay, so that's coming right from here. It says 54%. 54% of the chi-squared comes from here. So I just told them that's the most important finding that we found. Okay, 54% comes from right there. And then Houston has more than twice as many job openings in the area compared to the national average. So that's one way to say it. You could you just need to describe what it is, right? So you have Houston has 1,318 job openings between and as compared to what the national average says they should have of 609. Or what you can also do is do equals 708 divided by 609, and you can say that there is 116% more job openings than what were expected. Same thing with here. You can do equals the difference score divided by the expected score, and you can say there's 25% less than what was expected. Then once again equals the difference score divided by the expected score, and there's 69% less than what was expected for internet and tech, which that's a really big deal, right? 69% less, 116% more, and 25% less than what was expected. And so those are things that you can write in here. So more than twice as many job openings in the area compared to the national average, or more specifically, Houston has 116% more job openings in this area compared to the national average. The second difference contributing to chi-squared is the job openings in internet and tech. Houston is about 33% below, or better yet, there are 69% less jobs than what were expected. So Houston has about 69%, I don't know why I said 33, about 69% less job openings in this area compared to the expected national values, or national proportion. Job openings in this area compared to the expected national proportion. Which brings us, so we've interpreted chi-squared, and like I said, I didn't really care to interpret 10%. 10% is actually very much so could just have been a fluke at that point in time. But when we're talking about above 10%, those are things that we really need to note. The next thing that we need to do is determine the Cramers V. Cramers V is an effect size. And so we're going to look at Cramers V, and in order to look at Cramers V, we need to have a few pieces of information. First, we need the chi-squared value. So we've got the chi-squared value. Now we need the total number of observations, and then we need the degrees of freedom, which once we have that, we can do equals square root of chi-squared divided by, in parentheses, the number of observations multiplied by the degrees of freedom, which is 13.826 7, 9. So is this small, medium, or large? You can look at this fun little chart right here, and it'll tell you, what it's close to. So you look at the degrees of freedom. There's 7 degrees of freedom, and the question is what is this closest to? It's somewhere between a medium and a large effect size, right? Somewhere between a medium and a large effect size, which once again you can use a slightly different formula. And if we use a slightly different formula, the different formula is equals 0.1 divided by the square root of the degrees of freedom, which will give you the effect size based on each individual degree of freedom. Okay, and so I'm going to put 34. Okay, and then I'm going to drag this way. And then I'm going to drag it down. And you'll notice pretty much everything all stayed the same as what it was before, just with a lot more precision. And so the question is R V, what is it? Is it with 7 degrees of freedom? It is closer to a medium effect size, right? A medium effect size. So I'm going to say that is somewhere between a medium to a large effect size, but more closer to a medium effect size. So Cramers V. Cramer's effect size of 0.138 is a medium effect size, although a larger sample may be necessary. And if I could spell, there you go. May be necessary to observe the effect size. The results are noticeable and should be considered. Okay, so that is basically how you write the medium effect size. Okay, and then this finally brings us to the discussion portion, which once again, all that you're doing is going down this list one after the other, after the other, after the other. So what I'd suggest you do is just come right in here and say, okay, what was run? A chi-squared goodness of fit test was run. Well, comparing what? Comparing the frequencies between job openings by industries in Houston compared to the national proportion to determine if openings by job category are the same as the national proportion. Okay, or the national average. It should say proportion. National proportion. Okay, next. What is the p-value? The p-value, the probability of this occurring randomly, is almost non-existent, indicating the results are very trustworthy. And then, which we got that from a p-value of 0. They can give insight, about the possible factors influencing this. Okay, and this is where we, let's see. This is where we comment on the percent of chi-squared, because those are the factors that are influencing the chi-squared. The factor that's influencing 54% of the chi-squared is the architecture and civil engineering jobs, with 116% more job openings in Houston compared to the national average. The second difference contributing to the chi-squared value is the job openings of internet and tech, which all that I did was copy this and paste this from earlier. But Houston has about 69% less job openings in this area compared to the expected national proportion. Okay. Next, how noticeable are these results? These results are noticeable but may not be with a smaller sample size because it's a medium effect size. A medium sample size is needed to see the differences. However, with the larger sample size, we're able to establish that the probability of type 1 error is very low, or the probability of saying that we have a result and don't actually have a significant result is very low. And these results should definitely be used to provide insight for those who can benefit from them, because of how well these performed with this chi-squared test. So that's pretty much the end of that. chi-squared videos. Hopefully this was beneficial. There's a lot more that you can do with chi-squared, but we just haven't really touched it and won't touch it in this class. If you guys have more questions about the project, feel free to let me know, and I'll do my best to answer it.